Galileo Galilei. He looked up at the sky and challenged the world. There is a man buried in the Basilica of Santa Croce in Florence, resting beneath marble and silence, in a tomb the church did not want built. For decades after his death, they debated whether he even deserved a Christian burial. His crime was not theft. It was not violence. It was not heresy in the way most people understand the word. His crime was looking up. His crime was telling the truth about what he saw. His name was Galileo Galilei, and he was many things: a mathematician who could make numbers sing, a physicist who dismantled Aristotle with rolling balls and inclined planes, an astronomer who turned a carnival novelty into a window on infinity, a writer whose prose was so sharp and satirical it could have landed him a career in literature alone. He was a musician's son, with a musician's ear for harmony, a university lecturer who drew standing room crowds, a father who struggled to provide for his children, a friend to popes, and a prisoner of the same institution that once celebrated him. He was vain, brilliant, combative, generous, petty, fearless, and profoundly human. So how do we truly understand a mind this vast? How do we make sense of a man who did not merely contribute to science, but fundamentally altered the way our species understands its place in the cosmos? We do it the way he would have wanted, by looking at the evidence, by walking, step by step, through the key moments, the signature works, the decisive confrontations that defined his life. Not as a marble saint frozen in a textbook, but as a living, breathing man who made choices, took risks, and paid dearly for the things he believed. This is his story, told through the moments that mattered most. Let us begin. The Leaning Tower and the Falling Bodies, circa 1589 to 1592. The young professor who dared to drop things. Pisa, in the late 1580s, was a city caught between its fading medieval grandeur and the stirring energies of a new intellectual age. The Arno wound through it sluggishly, the summer heat pressed down on terracotta rooftops, and in the halls of the University of Pisa, young professors in black robes lectured from texts that had not changed in centuries. Aristotle reigned supreme. His word was not merely respected, it was functionally sacred. To question Aristotle in a European university at the end of the 16th century was roughly equivalent to questioning gravity itself. The irony, of course, is that gravity is precisely what Galileo chose to question. He was 25 years old, freshly appointed to the chair of mathematics at Pisa, the lowest paid professorship in the university, a fact he resented bitterly. His father, Vincenzo Galilei, was a lutenist and music theorist of considerable talent but modest income, and Galileo had inherited both the talent and the financial anxiety. He needed this position. He also could not stop himself from antagonizing the people who gave it to him. Aristotle had taught that heavier objects fall faster than lighter ones. It was intuitive. It seemed obviously true. A cannonball should hit the ground before a musket ball, if dropped from the same height, because it weighed more. For nearly 2,000 years, virtually no one had bothered to actually test this. Galileo did. According to his student and biographer, Vincenzo Viviani, and this is where we must flag the legend, Galileo climbed the Leaning Tower of Pisa and dropped two spheres of different weights simultaneously. They hit the ground at nearly the same time. The crowd below gasped. Now, most modern historians are skeptical that this specific demonstration happened exactly as Viviani described it. There is no contemporary account. Viviani wrote about it decades later, and he had a habit of burnishing his master's legend. But what is beyond dispute is that Galileo conducted rigorous experiments on falling bodies during this period, rolling balls down inclined planes to slow the motion enough to measure it carefully. And what he found was revolutionary. The rate of acceleration due to gravity is constant, regardless of the weight of the object. Air resistance complicates things. A feather falls slowly because of drag, not because it is light, but in a vacuum, everything falls at the same speed. Let me explain quickly why this matters so much. Aristotle's physics was not just a set of ideas about motion. It was a comprehensive worldview. Objects fell because they sought their natural place. Heavy things were made of earth, so they fell toward the earth. Light things were made of air or fire, so they rose. The entire cosmos was organized around teleology, purpose, intention, natural order. To demonstrate that Aristotle was wrong about falling bodies was to pull a thread that, if tugged hard enough, could unravel the entire tapestry. Galileo pulled that thread, and his colleagues hated him for it. He was abrasive, dismissive of traditional authority, and not shy about telling full professors that they were wrong. By 1592, his contract at Pisa was not renewed. He left, or was pushed, and headed north to the University of Padua in the Republic of Venice. It was, as it turned out, the best thing that ever happened to him. What this period reveals about Galileo's mind is crucial. From the very beginning, he trusted experiment over authority. He trusted his own eyes, his own hands, his own measurements. In an age when knowledge was something you inherited from the ancients, Galileo insisted that knowledge was something you built from observation. He was not the first to think this way, but he was perhaps the first to do it with such fearless, infuriating consistency. The telescope and the starry messenger, 1609 to 1610, the night everything changed. Venice in the autumn of 1609 was the most cosmopolitan city in Europe, a republic of merchants, spies, glassmakers, and diplomats, built on water and sustained by trade. Galileo had spent 17 productive years at the University of Padua, which fell under Venetian jurisdiction. He was well-paid, well-connected, and privately restless. He had a common-law partner, Marina Gamba, and 3 children. He was building instruments, tutoring private students, and quietly developing ideas about motion and mechanics that would not be published for decades. And then a rumor reached him that changed everything. A Dutch spectacle maker named Hans Lippershey had constructed a device that made distant objects appear closer, a tube with 2 lenses, a novelty, a toy. Galileo heard about it, and without ever seeing one, figured out the optics and built his own. Then he improved it, and improved it again. Within months, he had constructed a telescope with roughly 20 times magnification, far more powerful than anything the Dutch had produced. He demonstrated it to the Venetian Senate from the top of the Campanile of San Marco, letting senators peer at ships that were still hours from port. They were dazzled. They doubled his salary. But Galileo was not interested in ships. He was interested in the sky. On the night of January 7th, 1610, Galileo pointed his telescope at Jupiter. What he saw were 3 small points of light arranged in a line near the planet. Over the following nights, he watched them move. A 4th appeared. They were not stars. They were moons, satellites orbiting Jupiter, just as our moon orbits the Earth. Pause for a moment and consider what this meant. In the prevailing Ptolemaic model of the universe, everything orbited the Earth. The Earth was the center. The moon orbited the Earth. The sun orbited the Earth. The planets orbited the Earth. The stars were fixed on a distant crystalline sphere. But here were 4 bodies clearly orbiting something other than the Earth. Jupiter had its own system. The Earth was not the only center of motion in the cosmos. He published his findings in March 1610 in a slim, electrifying book called Sidereus Nuncius, the Starry Messenger. In it, he described not only the moons of Jupiter, but also the cratered, mountainous surface of the moon, not the perfect, unblemished sphere Aristotle had promised, and the fact that the Milky Way was composed of countless individual stars too faint for the naked eye to resolve. The book was a sensation. It sold out almost immediately. Galileo, overnight, became the most famous scientist in Europe. He named Jupiter's moons the Medicean stars, after the Grand Duke of Tuscany, Cosimo II de' Medici, a shrewd political move that secured him a prestigious appointment as chief mathematician and philosopher to the Grand Duke. He left Padua, left Venice, and moved to Florence. Some of his friends warned him. Venice was a republic. It had a long tradition of protecting intellectual freedom from papal interference. Florence was a duchy, closer to Rome, more vulnerable to church pressure. Galileo went anyway. He wanted prestige. He wanted freedom from teaching so he could focus on research. He wanted to be close to power. It was a decision that would cost him everything. But in those months of early 1610, none of that mattered. What mattered was the sky. Galileo later turned his telescope to Venus and observed that it went through a full set of phases, just like the moon, which was only possible if Venus orbited the sun, not the Earth. He observed sunspots and argued that the sun itself rotated, that it was not the immaculate, changeless body Aristotelian cosmology demanded. Each observation was a hammer blow against the old order, I do not feel obliged to believe that the same God who has endowed us with sense, reason, and intellect has intended us to forego their use, Galileo wrote. It is one of the most important sentences in the history of Western thought, and he meant every word of it. The Dialogue Concerning the Two Chief World Systems, 1632. The book that shook Rome. Florence and Rome in the 1620s existed in an uneasy intellectual tension. The Counter-Reformation was in full force. The 30 Years' War raged across Northern Europe. The Catholic Church was embattled, defensive, and deeply suspicious of anything that might undermine its authority, theological, political, or cosmological. And yet, within the Church, there were men of genuine learning, men who understood that the old Ptolemaic model was crumbling, men who might have been open to Copernicus if the argument were made carefully, diplomatically, hypothetically. Galileo was not a diplomatic man. In 1616, the Church had issued a formal admonition. The Copernican theory, that the Earth moves around the Sun, was declared foolish and absurd in philosophy and formally heretical. Galileo was privately warned by Cardinal Robert Bellarmine to abandon Copernicanism. He agreed, publicly at least, and spent the next several years working on other problems, including a lengthy dispute about comets that resulted in one of his most brilliant polemical works, The Assayer. But the Copernican conviction never left him. It burned quietly, patiently, like an ember waiting for wind. The wind came in 1623, when Cardinal Maffeo Barberini was elected Pope Urban VIII. Barberini was an intellectual, a patron of the arts, and, crucially, an old friend and admirer of Galileo. They had met, corresponded, exchanged pleasantries and ideas. Galileo believed, with some justification, that Urban VIII would be sympathetic to a carefully framed discussion of Copernicanism. He sought and received permission to write a book comparing the Ptolemaic and Copernican systems, provided he treated both as hypothetical and did not advocate for Copernicus outright. What Galileo produced was the Dialogue Concerning the Two Chief World Systems, published in February 1632. It is written as a conversation among three characters: Salviati, a brilliant Copernican who clearly speaks for Galileo; Sagredo, an intelligent and open-minded layman; and Simplicio, a bumbling Aristotelian whose arguments are systematically demolished over the course of 4 days. The book is a masterpiece of scientific argumentation and rhetorical art. Galileo marshals evidence from his telescopic observations, his experiments on motion, his understanding of tides, everything he had accumulated over 3 decades of relentless inquiry. The prose is vivid, witty, and devastatingly effective. He wrote in Italian, not Latin, deliberately making the work accessible to educated readers outside the university. He wanted the public to understand. But here is where the catastrophe begins. Simplicio, the character defending the Earth-centered cosmos, was widely perceived as a caricature of Pope Urban VIII himself. Whether Galileo intended this is debated. Urban had once made an argument about divine omnipotence that Galileo placed, almost verbatim, in Simplicio's mouth. It was either a spectacular misjudgment or a deliberate provocation. Either way, the Pope was furious. He felt mocked. He felt betrayed. A man who had been Galileo's protector became, in the space of weeks, his most powerful enemy. The book was banned. Galileo was summoned to Rome. What makes the Dialogue so remarkable is not merely its scientific content, but its form. Galileo understood something that many scientists still struggle with, that evidence alone does not change minds. You have to tell a story. You have to make the reader feel the absurdity of the old position and the elegance of the new one. You have to use humor, drama, and narrative momentum. The Dialogue is not a textbook. It is a performance, and it is that quality, the literary, theatrical, almost subversive quality of the writing, that made it so dangerous. The Trial and Recantation, 1633. The moment the world held its breath. Rome, in the spring and summer of 1633, was sweltering, politically treacherous, and unforgiving. Galileo arrived in February, aged 69, ailing and frightened. He was lodged initially in the Tuscan ambassador's residence, a small mercy, before being moved to apartments within the Vatican for the formal proceedings. He was not thrown into a dungeon. The Inquisition, contrary to popular mythology, did not torture Galileo. but the threat was always there. He was shown the instruments. He understood what could happen. The trial was not about evidence. No one in Rome seriously examined his telescopic data or tried to refute his observations of Jupiter's moons or the phases of Venus. The trial was about obedience. Had Galileo defied the 1616 injunction? Had he advocated for Copernicanism rather than treating it as hypothesis? The answer, to anyone who read the dialogue honestly, was obviously yes. The book was a passionate, barely disguised argument for the Copernican system. Galileo's defense, that he had merely presented both sides, was transparent and unconvincing. On June 22, 1633, in the convent of Santa Maria sopra Minerva, Galileo knelt before the assembled cardinals of the Inquisition and read his recantation. He declared that he abjured, cursed, and detested the opinion that the earth moves around the sun. He was 69 years old. He was broken. He was terrified. There is a legend, perhaps the most famous legend in the history of science, that as he rose from his knees, Galileo muttered under his breath, "Eppur si muove," and yet it moves. There is no contemporary evidence for this. The story first appeared over a century later. It is almost certainly apocryphal. But the reason it endures, the reason it has been repeated in every language on earth, is that it captures something essential about the man. Even in submission, the truth would not stay silent in him. He was sentenced to house arrest for the remainder of his life. He was confined first to the Archbishop's palace in Siena, then to his own villa in Arcetri, outside Florence. He was forbidden to publish. He was forbidden to teach Copernicanism. His dialogue was placed on the Index of Forbidden Books, where it would remain until 1835, 202 years. But something happened in Arcetri that the Inquisition did not expect. Galileo kept working. The Two New Sciences, 1638, The Prisoner Who Built the Future. Arcetri in the mid-1630s was quiet, rural, and exquisitely lonely. Galileo's villa, Il Gioiello, the Jewel, overlooked olive groves and the distant skyline of Florence. His beloved daughter, Virginia, who had become the nun Sister Maria Celeste, died in April 1634, just months after his return. He was devastated. He described the loss as leaving him in an immense sadness and melancholy. His eyesight, which had been deteriorating for years, continued to fail. By 1638, he was completely blind. The man who had seen further than any human being in history could no longer see at all. And yet he wrote, he dictated, he argued, he thought. The result was Discorsi e dimostrazioni matematiche intorno a due nuove scienze. Discourses and mathematical demonstrations relating to two new sciences, published in 1638 in Leiden in the Dutch Republic, safely beyond the reach of the Roman Inquisition. It is, in many ways, his greatest work. While the dialogue was the book that made him famous and brought him to ruin, The Two New Sciences was the book that built the foundations of modern physics. The two sciences in question were the strength of materials and the science of motion. The book returned to the questions that had fascinated Galileo since his youth in Pisa: how objects move, how they fall, how they resist breaking. It presented his mature understanding of kinematics, the parabolic trajectory of projectiles, the law of free fall, the principle that in the absence of friction, a body in motion continues in motion. These ideas would later be refined and unified by Isaac Newton into his laws of motion and universal gravitation. Without Galileo's groundwork, Newton's Principia would have been inconceivable. The book is written, once again, as a dialogue among Salviati, Sagredo, and Simplicio. But the tone is different. The political urgency is gone. The satire is muted. What remains is a kind of joyful, meticulous exploration, the voice of an old man who knows he is running out of time, but cannot stop being fascinated by the world. There are passages about the breaking strength of beams that read almost like poetry. There are thought experiments so elegant they feel inevitable. Galileo, blind and imprisoned, was doing the best work of his life. "You cannot teach a man anything," he once said. "You can only help him find it within himself." This is the philosophy that animates the two new sciences. It does not lecture, it guides. It asks questions and follows them wherever they lead, even into territory that was, for its author, personally perilous. He died on January 8, 1642, at the age of 77, still under house arrest. The Grand Duke of Tuscany wanted to build him a grand tomb in Santa Croce. The Pope forbade it. Nearly a century passed before a monument was finally erected, in 1737, when his remains were moved to their current resting place. During the transfer, admirers removed 3 fingers, a tooth, and a vertebra. One of those fingers, the middle finger of his right hand, is now displayed in a glass egg at the Museo Galileo in Florence. It points upward, toward the sky. The symbolism is too perfect to be accidental. Some say it was deliberate. A final, silent gesture of defiance from beyond the grave. Threads that run through it all. When you step back and look at Galileo's life as a whole, from the inclined plains of Pisa to the blind dictations of Arcetri, certain threads emerge, winding through every chapter like recurring motifs in a symphony. The first is the primacy of observation. Galileo never accepted an idea simply because someone important had said it. He looked, he measured, he tested. He trusted his senses and his instruments over the accumulated weight of 2 millennia of philosophical tradition. This sounds obvious to us now, but in his time, it was radical to the point of being dangerous. The second is the power of communication. Galileo wrote in Italian. He wrote dialogues, not treatises. He used humor, narrative, and vivid imagery. He understood that a discovery locked in Latin jargon, read only by a handful of professors, might as well not exist. He wanted the world to understand, and he crafted his words accordingly. He was, in every sense, a public intellectual, and he paid the public intellectual's price. The third is the willingness to confront authority. From his earliest days at Pisa, Galileo was constitutionally incapable of backing down from a fight. He challenged Aristotle. He challenged the Jesuits. He challenged the Pope. This was not always wise. It was not always strategic, but it was always honest, and it was always in service of what he believed to be true. The fourth is the union of mathematics and nature. Galileo famously wrote that, "The book of nature is written in the language of mathematics." Before him, mathematics and natural philosophy were largely separate disciplines. After him, they were inseparable. He showed that the physical world obeys precise, quantifiable laws, and that those laws can be discovered through careful experiment and expressed in mathematical form. This is the foundation of modern science. Full stop. The fifth is the cost of courage. Galileo's life is not a simple triumph narrative. It is a story of brilliance shadowed by persecution, of discovery met with punishment, of a man who was right and who suffered for it. He lost his freedom. He lost his daughter. He lost his sight. He never lost his curiosity, but the price of keeping it was staggering. The sixth, perhaps the most poignant, is resilience. Condemned, confined, blind, grieving, Galileo wrote his masterpiece. He did not stop. He could not stop. The universe was too interesting, the questions too compelling, the work too important. That refusal to surrender, even when every external force conspired to silence him, is perhaps the most inspiring thread of all. There is a question that echoes through 4 centuries, a question that was there at the beginning and remains with us now. How do we understand a mind this vast? We understand it by recognizing that Galileo was not a saint and not a martyr, though he has been fashioned into both. He was a man who looked at the world with terrifying clarity and refused to pretend he saw something different. He made mistakes. He misjudged people. He was proud to the point of self-destruction, but beneath all the vanity and the combativeness, there was something incorruptible, a devotion to truth that no threat could extinguish and no punishment could burn away. He showed us that the Earth is not the center of the universe, and in doing so, he paradoxically elevated humanity, because what he really demonstrated was that we are capable of figuring it out. We do not need to be told what is true by ancient authorities or powerful institutions. We can look, we can measure, we can reason, we can know. That is the deepest gift Galileo gave us, not a map of the heavens, but a method for reading it. Today, spacecraft bearing his name orbit Jupiter. His moons, Io, Europa, Ganymede, Callisto, are among the most studied objects in the solar system. Europa may harbor an ocean beneath its ice, and where there is water, there may be life. If we ever find it, the chain of discovery will trace back to a winter night in Padua in 1610, when a stubborn, brilliant man pointed a crude tube of glass at a bright dot in the sky and saw what no one had ever seen before. The Church formally acknowledged its error in 1992, 359 years after his trial. Better late than never, though one suspects Galileo would have had something characteristically sharp to say about the timing. His middle finger still points upward in its glass reliquary in Florence. Visitors stand before it and smile, sensing the defiance in it, the dark humor, the unbreakable will. It points toward the sky he loved, and the truth he would not abandon. It points toward the stars that vindicated him. It points, if you want to read it that way, toward the future, toward every scientist, every skeptic, every stubborn soul who has ever looked at received wisdom and said, "But is it true?" The universe does not care about our comfort. It does not arrange itself to flatter our importance. It is vast and indifferent and magnificent, and it operates according to laws that we can discover if we have the courage to look honestly at the evidence. Galileo knew this. He proved it with his instruments, his experiments, his prose, and his life. And for that, for the sheer, dogged, beautiful insistence on looking up and telling the truth about what he saw, we owe him more than a tomb in Santa Croce. We owe him the world as we understand it. Eppur si muove, and yet it moves.